All right. Good morning, everyone. Usual reminders. Our test 2 starts tomorrow. That's covering those sections, 2.2, 2.3, 3.1, 3.2, 3.4, and 3.8. So it starts at 12:01 a.m. Friday the 3rd, and it ends at 11:59 p.m. Monday the 6th. So you've got 4 days to cover that. I did notice this morning that my math lab said they're going to have some server downtime, whatever, something maintenance. I don't remember exactly, but they said something's going to be going on Friday. I think from like 1 a.m. to 9 a.m. Now that might take another hour or two. There's usually some runoff issues potentially, but just know that if you go and try and do this absolute first thing on Friday morning, you might have a little problem with my math lab, so maybe don't try and start doing it at 12:01 a.m. on Friday, or even 8 a.m. on Friday. Spend a little more time studying. The study guide has been posted. Remember that you get 2 hours and 2 attempts on each attempt of the test. That will, again, be available tomorrow. You won't see it for now, but it will be in my math lab right under where test 1 was, which I believe I had test 1 at the top, whereas the review was down in the chapter's worth of material, but all on the same page. Remember that I will put a spot for you to submit your work in Canvas, and that this is mandatory. And then a few other homework due dates. And I said I was giving you a small extension on 4.1 because of the testing. And in fact, we're going to go back to 4.1 and talk about one more topic that I mentioned in passing. And I thought it was in 4.3, but they covered it in 4.1 of this text. Our old textbook covered it in a later section. But it was something I mentioned. So just a couple more problems, and it's going to deal with finding that C value. All right, so in 4.1, we had our integration formulas, and we didn't get a ton of them. The first one we got was our power rule. Add 1 to the exponent, divide by the same value, but your original exponent's not allowed to be a -1, and by -1 I mean when the x is in the top. So this was the one case we have to pay attention to and not use that formula for. This wasn't an issue with derivatives, but it is with integration. We also had the constant rule. The integration of a constant was the constant times x, and that's because the derivative of a constant times x is the constant. We also said that coefficients of polynomial terms, or just basic functions, can just be pulled out of the integration. That's what this represents. It says that all you do is multiply that number by the integral of everything else. We also said additions and subtractions don't really affect integration, but multiplications and divisions do. We also pointed out that there is no product or quotient rule. We're going to have some fancier stuff to have to use. We'll wait on that. And then we also gave you the exponential and logarithmic integration rules. And when I say logarithmic, I mean the integral of 1 over x is the natural log of the absolute value of x, unless you claim that x is positive, in which case you don't need the absolute values. The integration of an e to the x, so both of these are natural exponentials, no base 10 or anything like that. The integral of e to the x is e to the x because the derivative of e to the x is e to the x. Just this extra c thrown in. And then we did give you a special case. This is kind of a special case of a formula we'll see later, but it's such a simple case, we go ahead and give you just the flat out formula. This is kind of like the chain rule for integration, but going backwards. But I don't want to say it is the chain rule because, again, it's a super simple case. So arguably we give you like 5 formulas in this section that we will continue to use over and over and over and over and over. They won't go away for the rest of the semester. You need to know them now, you need to know them tomorrow, you need to know them July 25th, you need to know them July 30th, etc. And we did, like I said, a whole bunch of examples. And I want to point out something before we do this last topic. Oops. I want that to be in black. The integral of e dx. This is a problem I intended to do last time and skipped. I was going to save it for the next section, but I'll just go ahead and do it now. The integral of the integral of e dx. This right here is not the same thing as this, e to the x. It's not the same thing as this, e to the 4x, e to the 2x. This, believe it or not, does not use this formula. The reason being, this formula is for things that are e to an x, or e to a 5x, or e to a 7x. That e has to have a variable in the exponent. This e does not have a variable exponent. So there is no variable exponent, which means this is like the integral of a dx. It's just a constant. We said that the integral of a constant is just that constant times a variable plus another new constant. So the integral of e dx is ex plus c. Because e is really just a number. It's 2.7 and some change. So this is just the integral of 2.7. That's like integrating 3 or 5 or 9. It would be 3x or 5x or 9x or whatever number you've got. So make sure you see the difference in this versus this. This is just a constant in the first one we did. This is an exponential, which has the exponential formula because of that. Okay. So, last official topic of the section. Please don't do that. And it's going to do that. Arg. What in the world? Every time. Trying to decide how I want to do this. I'll just put it at the end. It's fine. It's fine. Finding the constant of integration. How do we find the c? You're given an initial condition. On the function after it has been integrated, find c. An initial condition looks like capital F of A equals B, or little f of A equals B, depending on the original problem. If your problem is this, oops, my dx. If your original problem says that the function they gave you is a derivative and you're finding the actual function, and you have your constant added in, the initial condition would look like this. F of A is equal to B. But if it looks this way, if we give you the original thing written as a normal function, not its derivative, when we integrate a regular function, that's when we go to the capital letter. And in that case, the initial condition would be capital F of A equals B. Again, it just depends on the original notation. Did they give you a function written as a derivative, or did they give you just a function written as a function? Because if they give you the function written as a derivative, when you integrate, you don't use a capital letter. The integral of this is this because the derivative of this is this. But when they just give you a regular old function and they say to integrate, this wasn't a derivative, so we don't go to a, skipping out on writing that little dash. That's when we go to the capital letter. So the hierarchy is like capital letter, lowercase letter, F prime, F double prime, F triple prime, working your way down. So again, you have to pay attention to the notation, but you're never going to be plugging an initial condition into the original function that you were given. You're going to be plugging it into the integrated function. That's the main thing to account for. Either way, you're plugging in after integrating. Otherwise, you won't see the C. Sorry for the terrible pun, completely unintentional. So how would you solve for it? Now, the solving of this is not difficult. It's straight up algebra. It's plug in a number and then solve for a variable, the variable being your C. So let's try it out. Let's see, what example are we up to? Example 6. And let's say a little lower, first of all. Integrate the given function. And find the constant of integration. A. We're going to write this as f prime of x is equal to x squared plus 1. And then our initial condition is going to be f of 0 is equal to 8. See, this doesn't say f prime of 0 equals 8. This says f of 0, and the given function was an f prime. Someone just asked if anyone else hears a clicking noise every time I begin to speak. Please feel free to answer that in the chat if you do. I'm not sure what's happening. I know the house behind me is doing some pretty major construction. I hear like some banging, but I have a feeling that's not the clicking you're referring to. Is this, do you hear that clicking? Is that what it might be? That's my pen. Maybe I'm just being a little aggressive with my pen today. No, you know that noise. All right, well, I'm sorry. I hope it's clear enough for me to hear. I'm sorry if it's annoying, all these fun things. If it continues to be a problem, I'll pull out my headset again, but I'd rather not if I don't have to. Okay, so this is the function we're going to integrate. So we set this up as the integral. I'm going to switch my color though. The integral, and I got to put it in parentheses to make sure that the dx part is set up correctly. So the integral of x squared plus 1, then dx. So this is just the power rule. You're going to add 1 to the exponent and divide by the same value. So adding 1 to 2 is 3. So you get x cubed over 3. Again, you add 1 to the exponent, then you divide by the same value. Plus, this is a constant. When we integrate a constant, you just throw the variable next to it. So I'll write the 1 to be clear. So this is the 1 that we originally had, and you just give it an x. And if you don't believe that, take the derivative of 1x, you should get 1. That is something I highly encourage you to do while you're starting to learn this integration process. Do this and then go backwards to check it. But don't forget our plus c. There's nothing else we can simplify with this. So that says that f of x, because we integrated f prime, this is our f of x. is equal to x to the third over 3 plus, I'm not going to write the 1 now, plus the c. So again, that's a lowercase f. It's not the prettiest f. I want to make sure you can tell that's a lowercase. There we go. So now all we do is we're going to use this initial condition and plug the 0 and the 8 in appropriate spaces. This is where the x goes, the 0. So the 0 is going to be the x's. Then the 8 is what the function turns into. So you're going to turn this into the 8 because we're actually showing that the function value is 8. And then 0 is going to go here and here because that's what the x is. So the f of x becomes the 8, the x's become the zeros. So again, f of x is going to be 8 when x is 0. So plugging all that in will give us the following. Instead of writing f of x, I write 8, then the equal sign. Instead of x cubed over 3, it's 0 cubed over 3. Then plus instead of x, it's 0. But the c stays. We don't plug anything for the c in. We're finding the c. That is what's going on here. Well, 0 cubed over 3 is 0. 0 divided by anything is 0. 0 plus 0 is 0. The whole right side is 0 except for the c. The left side is 8. So you get 8 equals c. It's almost no work to do, in fact. It's extremely simple. So all we do is go back in, plug this number in where we had a c written before. That's going to go there. So our function, f of x, which was the integral of f prime, and accounting for the initial condition, is x cubed over 3, or 1/3 x cubed, plus x plus 8. Now that c could have a negative sign. That's always possible. Then if this was a negative 8, then this would be a minus 8, is all I'm saying here. So there is no more plus c. The c could also be 0. These are all possible scenarios. So this is how we find a constant of integration. Let's try another, and let's do it with the other notation. Instead of giving you f prime, I'm going to give you f of x. So f of x is equal to, let's go with 6x squared minus 4x plus 2. And I'm going to tell you that f of 1 is equal to 9. Capital F. I'm sorry, I'm messing up. Capital F of 1 is equal to 9. See, because we're supposed to be integrating the original function, integrating a regular lowercase f gives us an uppercase f. That's the hierarchy. So capital F of x, and I'll even write this extra step at the beginning, is the integral of f of x dx. So that's the integral of, can I do this? 6x squared minus 4x plus 2 dx. Is this okay? No, it's not okay. It's not okay because we don't have the parentheses is all. And then we just straight up apply our power rule. All of these are polynomial terms, so just power rule it. The 6 and the 4 won't have any effect, just leave them as multipliers. The x squared, you'll add 1 to its exponent. 1 plus 2 is 3. And then you divide by the exact same number that you just got. Again, that's the power rule from earlier. Minus 4, leave the minus 4 there. Now there's no exponent written here. If we don't see an exponent on a variable, we assume it's a 1. So there's an implicit or implied 1 there. 1 plus 1 is 2. So this becomes an x squared, and then over 2, because these numbers must match. Then plus, The integration of 2, since that's a constant, it's just 2x. And then we, of course, have our plus c at the end, which is kind of hidden there, but there it is. So our integrated function, the 6 divided by the 3 is a 2, so that's 2x cubed, minus the 4 divided by 2 is a 2, and that's an x squared, then plus the 2x, lots of 2's, plus the c. Now, last class, we would have stopped at this point. We wouldn't have been given the initial condition, but now we have it. We know that if you plug in 1, the whole thing turns into 9. So if you plug in 1 here, here, and here, this whole thing should be equal to 9. So in other words, f of x is equal to 9 when x is equal to 1. So this function becomes 9, and the x's become 1s. So 2 times 1 cubed minus 2 times 1 squared plus 2 times 1 plus c. And from here, it's just straight up algebra. 1 cubed and 1 squared is 1. 2 times 1 for all of those is 2. So that's 9 equals 2 minus 2 plus 2 plus c. The 2 minus the 2 in the front cancel. So you just have 9 equals 2 plus c. Subtract 2 on both sides. And you'll get, sorry about that, 7 is equal to c. So our integration constant is 7. So the answer is 2x cubed minus 2x squared plus 2x plus 7. The initial condition gives us one answer instead of literally trillions of answers. The answers before, when we had a plus c in there, that c was undetermined. Because remember, when you take the derivative of a constant, you get 0. So that constant is there because we don't know if there was originally or not. But when we're given an initial condition like this, capital F of 1 equals 9, when a lower case function is prescribed, or a lowercase f when the derivative is prescribed, now that is what enables us to figure out what the original constant would have been. So when you go and take this derivative, you will still get the original function because the derivative of 8 goes away. The derivative of this 7 goes away. Not all problems are given an initial condition. Some of them are, some of them are not. So if you aren't given an initial condition, you will have a C in the answer. When you are, you won't. Most word problems usually have an initial condition. And I've got a couple word problems I'm kind of setting to the side for now that I want to come back and do once we get through some more material. But I want to get the basics done first before I get into word problems and kind of complicating things, if you will. So with that being said, we can call 4.1, excuse me. I'm still thinking the old textbook in my head. 4.1 completed. All right. So let's make a new document. Let's hit enter for about 17 pages worth. I'm about sick of that issue, right? Okay. 4.2. This title is Antiderivatives as Area. I mentioned last time that the way that we cover this section is going to be interesting, to say the least. Most of the homework problems in here go through a much more complicated process of approximating area via what we call Riemann sums. And what exactly a Riemann sum is, we're going to get into. But the problem is they're very, very time consuming. So it's not a problem that I really like to discuss in super great detail and give you tons of homework and tons of test questions on. However, it is still an important concept that ties in what we were just doing to the geometry of calculus, because when we talked about derivatives, we figured out that they were slopes at points. Well, it turns out that integrals, or antiderivatives, whatever name you want to give it, they relate to, well, spoilers, area. So derivatives are used to talk about the slope of a function. Antiderivatives, or integrals, are used to talk about the area of a function. And you might go, well, why would you ever want to know the area of a function? What's the point of that, right? Well, let's have a leading example just to kind of set up this concept. We got somebody that's going to be driving 15 miles an hour on a little motor scooter. So we got Bob drives, and I think the textbook's name's Emma. I don't care. Bob, Emma, Jane, whatever. Bob drives at 15 miles per hour. He's on a little scooter for an extended period of time. And when I say this, my brain just goes to a classic movie, Dumb and Dumber, to people on a scooter for a very, very, very long time. Sorry, I know I'm a little silly, but can't help it. So Bob drives at 15 miles an hour on his scooter for an extended period of time, an hour, a day, a month, something like that. Let's ask a couple of questions. How far has he traveled in 1 hour? How far has he traveled between I'll fix that in a second, the first and second hour? How far has he traveled cumulatively between the first 2 hours? And can you think of a function that gives the total driving distance? Picture's worth 1,000 words. All right, so Bob drives 15 miles an hour for an extended period of time. I don't think that a lot of people are at this level are going to have a hard time figuring out that if you're driving 15 miles per hour, you're going to go 15 miles in 1 hour. Oh, I didn't fix my typo. Also give you a few minutes to write all that. If you drive your scooter at 15 miles per hour, that means in 1 hour you go 15 miles. It's literally 15 miles per 1 hour. Then, how far has he traveled between the first and second hour? This is asking the same exact question, just phrased slightly differently. It's asking how far does he travel in an hour, but specifically from, minute number 60 to minute number 120. Well, that's still 1 hour's worth of time, which means he still travels 15 miles. How far has he traveled cumulatively between the first 2 hours? Well, 15 miles for the first part, 15 for the second part, so 30 miles. You just add them up. Can you think of a function that gives the total driving distance? So that's not really related to question B. It's more related to questions A, and C. After 1 hour, he went 15 miles. After 2 hours, he went 30 miles. So for part D, we're trying to think of some function of time. So let's use t for time. So that time is going to be in hours. That whatever this function is involving t, if you were to plug in 1, you'd get 15, and if you were to plug in 2, you'd get 30. Now, if we had lots of time together, we could sit here and try and do slope analysis and all sorts of things, but I hope that you've had enough practice with linear functions with no intercepts to figure out that this is just 15 times t. If you plug in 1, 15 times 1 is 15. If you plug in 2, 15 times 2 is 30. And this works even further. 3 hours, 15 times 3 is 45. He would go 45 miles, 15 in the first hour, 15 in the second, 15 in the third, for a total of 45. So f of t is in miles. T is in hours, f of t is in miles. Now, I came up with this kind of off the top of my head, if you will. I could have, again, like I said, used point analysis, done 1, 15 and 2, 30, found the slope of that, assumed that this was a proportional function, which makes it linear, and all sorts of good stuff. The point of all this is, how do you go from just this fact of 15 miles an hour to get this answer of 30 miles? That's what calculus is building us towards. How can we just know that he drove 15 miles per hour and get 30 miles without making this function up off the top of our heads? How could we find this function using calculus? I am writing terribly there. I want to type it. Well, remember that velocity is the derivative of position. D prime of t is equal to v of t. This means if you go backwards, if you think antiderivatives, the integral velocity is position, which is how far you've gone. i.e., the integral of velocity is equal to distance, or position. Now, when you integrate, of course, you've got this integration constant thing going on. So this suggests that if we integrate 15, which was the velocity, it's a constant speed, there's no variable with it. Our velocity was 15. So if we integrate this, we should be able to get a function that would tell us our position. So let's integrate this. The integral of 15 dt. Now that's a constant. The integral of a constant just gives you the constant times the variable, but this isn't an x because we're integrating over time, dt, so this is 15t plus c. Notice that this thing right here and this thing right here are the same. So that's a good sign, but what about this plus c issue? What's going on with that? So what's up with that plus c? Let's Pause on that idea. And finally get to the picture is worth 1,000 words bit. Finally. All we've done so far is we've used basic logic and reasoning to get that, oh, he went 30 miles in the first 2 hours. We also built a function based on simple algebra skills. We made an association between derivatives and integrals in relation to our distance, velocity, and acceleration formulas, their derivatives with respect to each other. So if the derivative of distance is velocity, the integral of velocity is distance. We integrated the function, we got a familiar looking piece, but then there's extra constant in here. So if you plugged in a 2, this 15 times 2 would be 30, which probably makes you think we'll just ignore the c. Like I said, pause on that idea. It's not that you ignore the c. It's something happens to it that we'll get into in the next section. But now let's again go to the picture's worth 1,000 words. Let's graph velocity function versus time. Now the velocity function is constant, so it's a horizontal line. Height 15. And we'll do this. So velocity versus time, velocity, time. So a velocity, it's constant at 15 miles per hour. So here's our 15. And no matter what the time is, whether it's 1 hour in, whether it's 2 hours in, whether it's 3 hours in, whether it's 1,000,000 hours in, this right here is our velocity function. It's just 15. It's not 15t. That was the position function. The velocity was just 15 miles an hour. It was constant. Now what I want us to do is, let's imagine that we drew vertical lines on the 1 and the 2 separately. So let's draw vertical lines at x equals 1, which is 1 hour, then x equals 2, which is 2 hours. And again, we're going to do this as separate problems. So let's draw a vertical line here. And I'll do it dotted because it's not really anything. And what I'm going to ask you to do next is find the area of the rectangle surrounded by the axes. Find the area of the rectangle surrounded by the axes. What I mean is this area. It's a rectangle. If you don't know how to find the area of a rectangle, I'm terrified. It's length times width. So this thing has a width and a length, or height and width, however you want to say that are very predictable. You're starting at 0 here and 1 here, so that width is 1. I'm going to do this in blue. So again, 1 is this width right here. And then the height of the box, it's going from 0 to 15, so the height of that box is 15. So that little area, let me call this area 1, would be 1 times 15, which is 15. Now guess what? The fact that this is a 15 is not a coincidence. Remember when we found out how far I traveled in the first hour? It was 15 miles. And this is a 15. That's not a coincidence. Now let's do the other one. So now we'll do this region, which we'll call little a2, a little 2. And that is very similar to the last one. This width right here from here to here is 1. I should have done it in a different color. Let's pick a different color. Let's go with dark green. So this distance right here is still 1. This vertical distance is still 1. So area 2 is 15. 15, the height is 15 before anyone corrects me. Sorry about that. Is 1 times 15, which is 15. And guess what? That's going from hour 1 to 2. It's not a coincidence that how far he drove from hour 1 to 2 is 15 miles. What I'm hinting at is that these areas are how far Bob has gone from hour 0 to hour 1, or from hour 1 to hour 2. Now let's do the whole thing. Let's go from 0 to 2. So I'm going to redraw everything. So here's the function at a height of 15 to represent our speed of 15 miles an hour. Then we're going to go from 0 to 2. I didn't do the dotted line along the axis the first time. It's not really important. I mentioned it. We're going between 0 and 2, so we're finding this area. So this width would be 2. We're going from 0 to 2, so that's 2. The height is 15. So the area, let me just call it capital A, no subnotation, would be 2 times 15, which is 30. And guess what? It is not a coincidence that the answer of how far he traveled between the first 2 hours cumulatively was 30 miles. This shows that the area under the curve, and I'm saying curve in quotes because yes, these are lines, but we're generalizing the area under the curve, of a function. It's just the integral of the function from 2 given x values. The area under the curve of a function is the integral of the function. Derivatives are slopes, integrals are areas. Now, in the last section, we never actually did any areas because we didn't say to go between these two values. It's only area when we tell you to go between two values. See, on this one, we went from 0 to 1, and then we went from 1 to 2. Then we went from 0 to 2. Again, in the last section, we never plugged in two x values. You might say, well, you plugged in 1. Yeah, we did 1, but not 2. That 1 was just an initial condition that enabled us to find c. In fact, when you're doing these problems, c is completely irrelevant, as we'll spoil in the next section. Now, you might be thinking, well, Mr. Beckner, these are just lines. How does this actually tell me that this really works? That the integral function can be used to find the area under a curve. So while you're not necessarily trusting me yet, let's build up our functions. Let's do a little more of a complicated one, then a little more of a complicated one, and see what we can get out of this. So let's do another example. Call that example leading example. So we'll just go, I guess, example 1. Example 2. I lied. In quotes because, like I said, not necessarily assigning everything, but this is still important conceptually. So for f of x is equal to x. I don't need to write this, I can type it. For f of x is equal to x, the standard linear function with a slope of 1 and no y-intercept. Show that the area under the curve, again, curve in quotes basically, from 0 to 4 agrees with its integration. So let's do the integration first. If f of x is equal to x, capital F of x is the integral of lowercase f of x. So we're integrating x times dx, which is x squared over 2. This is an x to the 1, so you add 1 and divide by the same value. Again, these numbers have to match. And then you go plus c normally. Again, as I said, coming up, we'll talk about why the c is going to go away very short. So there's our integral. So if little f is x, then uppercase F is x squared over 2 plus c. Well, let's do the graph. Here's a graph. And, excuse me, I'm really only worried about the positive region. We're going from 0 to 4. This is the line y equals x, or f of x equals x. At 1, we have a height of 1. At 2, we have a height of 2. At 3, we have a height of 3. And then at 4, we have a height of 4. So 1, 1, 2, 2, 3, 3, 4, 4, those are 4 points of that line. You only really need 2 of them, but you get the point. So we want to find the area under the curve from 0 to 4. That's why I stopped at 4. Now, this thing starts at the origin, and then it goes up to 4. So if you want to do that little divider, that's where we're stopping. So the area that we're finding is this right here. This is our area. Now, I didn't give you any physics relationship to this, just math. What does that shape look like? I just spoiled it, didn't I? This sloped side along with this vertical and horizontal side, that looks like a triangle. Triangle areas are predictable. It's 1/2 the base times the height. Well, this triangle has a base of 4 from here to here, and it has a height of, well, coincidentally, 4 as well. They don't have to match. So that area should be 1/2 of 4 times 4. Half of 4 is 2, 2 times 4 is 8. So the area under this, quote, curve or line, as it is this time, is 8. Now let's go back to the previous example. The areas, the 15s and the 30s, seem to be us going from 0 to 1 or 1 to 2 or 0 to 2 respectively. Let's ignore the 1 to 2 part. Let's just look at the 0 cases. So from 0 to 1, it was 15 miles, and that was the area under the curve. From 0 to 2, it was 30, and that was the area under the curve. The c didn't seem to have an effect when we went from 0 to something else, when we went from 0 to something else. So going from 0 to 4, because that area is 8, that suggests that if I plug in 4 to this function, the answer is probably 8. So let's say, does this match f of 4? Excuse me. So capital F of 4, remember we're using this function, not the original one. It's x squared over 2, so 4 squared over 2 plus c, which is 16 over 2 plus c, which is 8 plus c. The fact that this is an 8 and this is an 8 means that we're probably on the right track. So again, note c becomes irrelevant. Irrelevant. It's not gonna matter. So now you're thinking, all right, well, why would we ever do the calculus? Why don't we just do this geometrically? Because if these aren't a horizontal line or a sideways line, this is insane. Trying to find the formulas for areas under a parabola or a cubic or a quintic or a rational or a radical function, you're not going to know these. These were super basic shapes. We have a rectangle and a triangle. Most of the time, we're usually finding the area under an actual curve, like f of x equals x to the third minus 5x squared plus 2x minus 1. And if you go to graph that, x to the third minus 5x squared plus 2x minus 1. So maybe you want to find the area under this curve from 0 to 4. So you'd be finding the area under or above. It could be above too if it's below the x-axis. So you're trying to find this shaded region, like 0 to 1, 2, 3, 4, kind of stopping here. Here, sorry, I'm pointing at the wrong thing. What formula gives you the area here? I have no idea. You'd have to integrate it. That's why we don't want to just graph it and then try and use basic geometry, because 99.99% of the time, you can't do that. So for now, what could we do using geometry? Using basic geometry, we can approximate the area under the curve by dividing it into many small rectangles. There are many other methods than this. But this is what we will use. Again, they call it a Riemann sum. R-I-E-M-A-N-N. I couldn't remember if there was 2 N's or not at the end. I had to look it up, and it is 2 N's. So again, this is known as a Riemann sum. R-I-E-M-A-N-N. S-U-M. Let me show you what we're talking about here. So you got some function. And you're going to go from A to B. So 0 to 5 or 1 to 12, whatever. And this is your curve. So this is our original f of x. And we want to find the area from A to B. So I'm gonna show the area we're trying to find, but then I'm gonna erase these diagonal lines. And I drew that too far. This is showing the area we're trying to find. but we're going to approximate it. We can't do a Riemann Sum and find this exact answer using these little rectangles. So what we do is we divide this up into a number of regions. So we'll have a rectangle, let's say this height here, and I'm going to try and make this as even as I can. I'm going to make them pretty wide. So here's your first rectangle, and then your second rectangle, and I'm going to change the colors each time. So the second rectangle would look like this. Then the third rectangle, I'm just going to keep going between red and blue, would look like this. Then the fourth one would look like this. The next one would look like this. And I'm getting a little wider at the end, but that's okay. It's not the point. And then this. So using basic geometry, we can approximate the area under the curve by dividing it into many small rectangles. So we find the area of all these rectangles because those are easy to find. It's just length times width. So you take this width times this width times this height, this width times this height. Now notice that these rectangles, because the function is at different heights on the left and the right side, you can't have them touching. So like this first blue one is below the curve here. This one is about the same because of it going up and then back down. But then the rest of these are actually a little over. So this first one is an under approximator, but then the third, fourth, fifth, and sixth are over approximators. Now this was attaching them to the left side. So I've anchored these to the left side. So again, I'm having points here, 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 and here. Those are the heights that we would actually use for the calculations. So this is a left side approach. Or, let's do this one more time. I'll try and draw this the same as best as I can. That's already a bad start. Good enough. So this is a left side approach. This will be the right approach, right side approach. So we're going from A to B. B was on the bottom. There we go, blue. So now I'll use the right side. So when I make my first rectangle, instead of starting from here, I'm not going to do this. This is no longer going to be the rectangle. I'm going to anchor it to the height of the right side. So in other words, this point needs to be a little higher. Then for the next one, again, we're going to use the right height. So it appears to be about here. I got 1, 2, 3, 4, 5, 6 of these. Then we'll go with a blue one. Let me extend that. So now the right height, which is about here. I know that one looks a little wider. Again, just forgive my poor artistic ability with this. And then again, right height, so about here. And the right height, which is about here. And then the last one, the right height is definitely here. There we go. So again, the left approach, you use the heights as the left side of the rectangles. The right approach, you use the right side of the rectangles for your points. Does it matter which one you use? Well, it depends on whether you want an approximation that's too big or too small. With this left approach for this example, there's a lot more over approximations, like this one's a little too much, a little too much, a little too much, a little too much, whereas this one's just a little to less, not quite enough, if you will. So this one probably over approximates the area, whereas this one, most of the rectangles are below. There's only one that's above, and that's this one. So this would probably under approximate it. Now it depends on your function. All left approaches don't over approximate, some of them under. Same for right, that not all of them under, some of them over approximate it. And what's cool is another extending tactic, like I said, there are many of these tactics. What you can do is do a left approach, do a right approach, average them, and I bet the average is probably closer than the left and the right approaches for normal acting functions. Notice I'm throwing quantifiers out there, it's not a guarantee. Instead of using rectangles to approximate these areas, you can use trapezoids. So you can actually add on a little triangle to the top of each of these and add or subtract them. So like this one, you could add a triangle to it and add it. This one, you could subtract this little triangle. That would give you an even closer approximation, but it's even more work. And we call that the trapezoid method. So one thing that's consistent with these is the widths must be the same. Where's my mouse? The widths must be the same for each rectangle. Choose or given. You then find the x values. Plug in to find heights based on the width of each rectangle. Call the width of each rectangle delta x. That little triangle represents a change. We've used that symbol to denote slope before, right? Triangle y over triangle x was the change in y over the change in x. And this represents the change in x values. Typically, smaller this delta x is, which is the triangle means delta, the better the approximation. So if you use a width of your rectangle as 5 versus using a width of 1, a smaller width means you're going to have more rectangles, which means it'll be a more accurate approximation. If you use a width of 0.1 or 0.01 or 0.001, it's going to keep getting better and better and better. And some of you might already know or have an idea what I'm leading to. Back when we were doing derivatives, we took the distance between 2 points and we slowly and slowly merged them together until they became the same point. That's the exact idea we're doing here. We're going to take that delta x and we're going to make it infinitesimally small. We're going to take it to 0. And when we do that, it turns into that dx thing, and it ends up giving us an integral. That's the ultimate aspect of all this. But let's do one example with this Riemann sum, just to give us an idea of how this would flow. We'll do it with a simple function, and then I think we can call it for this section. So example. Approximate the area under the curve x equals 0 to x equals, let's go with 5. With delta x being 1, function f of x equals x squared. Using a left-sided approach. If you want to have fun with this, do a right-sided approach and compare your answer. So we're going from 0 to 5 with a width of these rectangles being 1. So let's draw up the picture so we have a good idea of what we're going to be looking at. We're going from 1 to 5. The height of 5 for x squared is going to be 25, so I know I need a 25 way up here at 1, 2, 3, 4, 5. Now, I should really have these a little more squished together on the horizontal axis, but I want you to be able to see the details of the triangles. So then we know that f of 4 squared is 16, 1 squared is 1, 2 squared is 4, 3 squared is 9. So, trying to think how I want to do this. This is probably about 16. Then we'll have this at about 9. Then about 4, and a height of 1. So there's our x squared graph. Basic parabola, everyone should know what that looks like. Forgive me if the heights aren't lined up perfectly. Not the point of the problem. So we want each of these widths to be 1. So going from 0 to 1 would be one rectangle. Going from 1 to 2 would be one rectangle. Going from 2 to 3 would be one rectangle. From 3 to 4, from 4 to 5 would be our one rectangle. Again, f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9, f of 4 is 16, f of 5 is 25. Now we said to do a left-sided approach, which means we're anchoring to the left sides to draw our rectangles. And I'm actually going to work from the right side backwards because the first one might throw you off. So when I want to find the last one, when I want to find, well, first of all, we're going overall from here to here. So this is the area we are finding. Forgive me for being a little over-exuberant there. But we're approximating. So for the right triangle, the furthest right one, it has to be this. This has to be the triangle because we're using a left-anchored approach. If I was using a right-sided approach, I would have done it this way instead. So that's the first rectangle from the right. Again, I'm working backwards. The next one, it would be this. Again, each of these delta x's is 1. Each of the widths of these is 1. Then this would be the next one. Anchoring it to the left side of the curve. Then this would be the next one, anchoring it to the left side of the curve. And the last one, that's a height of 0. There's actually no rectangle because if you have a height of 0, I mean, that's a non-existent rectangle, right? If I had done a right-sided approach, there would be a rectangle on that one and it would have a height of 1. So this is definitely going to be an underestimator because we don't have a rectangle here, so this area is completely missing. This one's going to be missing this little chunk. This one's missing this chunk, and this chunk. So this will be an underestimator. Now let's find all of these. So again, each of these little widths, this shows that the delta x is equal to 1. This shows that the delta x is equal to 1 because the widths are 1, because the widths are 1. I'm not going to write it for all of them. So the total area should be approximately 1, 2, 3, 4, 5, the sum of all these little areas, A1 plus A2 plus A3 plus A4 plus A5. The area of the first one, there's no rectangle, so it's 0, plus the area of the second one, this would be A2, that has a width of 1. All of them have widths of 1, so 1 times. and then the height. The height of this rectangle is 1. Again, it's all widths times heights. All of the widths are 1. Plus, then the next one, this is area 3, still has a width of 1, but its height is 4. See, 4. Plus, the fourth one still has a width of 1 times, and its height is 9. 9. Plus, and then this last one over here, the width is 1 times its height, which was 16. We actually don't even use the 25. If we did a right-sided approach, we would, but it was still nice to know that. So this is 0 plus 1 plus 4 plus 9 plus 16, which is 5. 5 plus 9 is 14. 14 plus 16 is 30. Again, this is the approximate area. Is it 30? No. Is it close to 30? Yes. In fact, I'll tell you the exact answer. It would be 41 2/3. So 41 2/3 is kind of close to 30. You know, it's 10 off. That might not make you too happy. And that's because these rectangles are pretty large. If you wanted a better approximation, then you'd use delta x equals maybe a half or 0.1 or 0.001. But the smaller you make your delta x, the more rectangles you're going to have. If I make the delta x a half, that means I'm going to need 10 rectangles. If I make the delta x is 0.1, so if your width is a half, that means it's going to take 2 rectangles to go to the first one, so 10 rectangles needed. If you let your delta x be 0.1, so that means it takes 10 of them to go a whole unit, which would be 50 needed. If you use 0.01, that would be 500 rectangles. You can see why this is annoying to do by hand. Now here's the thing, when you're talking about computers, these are amazing and wonderful techniques because computers, in the snap of a finger, can do that for you. You can go to 0.01 or 0.001. In fact, your TI-83 can do this. And I don't want to show you yet. But again, this is just showing how we kind of build to the real calculus. So this Riemann sum for rectangles. The left side approach says the area is approximately f of a times delta x plus f of a plus delta x times delta x. You know what? Let me write this slower so I don't have to squish everything. Sorry about that. It's about f of a times delta x plus f of a plus delta x times delta x plus f of a plus 2 times delta x times delta x plus, and then you keep going until you get to f of b minus delta x times delta x. What am I doing inside of the functions? I just keep adding the width. So f of a in this instant was 0, and the delta x was 1. So if you add 1, you get to the next function value, f of 1. And you're going to add it one less time, because if you added it one more time, you'd be going too far. So that's why you start at f of a being the height. So this is just a bunch of heights times width. That's a height times a 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 width. You're just adding up a bunch of heights times widths. There's some summation notation used for this. Again, I'm not really going to get into that. We're just going to leave it as is for now. What did I want to say? There was one more thing I wanted to say in this section, and I cannot, for the life of me, remember. Oh, I know what I want to do, the right side approach. So we did the left side approach. Now let's do the right side approach. The right side approach. Ooh, that was ugly. Let's try that again. That was a little wider before, wasn't it? That's good enough. Okay, so here's your 5. That height is 25. Let's go 1, 2, 3, 4. That's not good. 1, 2, 3, 4. That's better. And the heights, that's got a height of 0, then a height of 1. Then this has a height of 4. This has a height of 9. This has got a height of 16. And then way up there, a height of 25. So now we're going to do right-handed rectangles. Same delta x, we're still going to do a width of 1. But now we're going to use the right side. So for this first one, instead of trying to anchor it at a height of 0 and making no rectangle, we're going to anchor it from the right side, which means we have a height of 1. So there's our first one. Then our second one, anchoring it from the right side, you have this as your rectangle. And the next one would look like this. Then the next one would look like this. And then the next one would look like this. So this is definitely going to be an overestimator. All of these areas, this area, this area, this area, this area, this area, that's too much. Just like last time, all those little spaces were too little because they were below. See, that was too much. These spaces right here, this was missing section, missing section, missing section, missing section, completely missing. Right, so again, each of these little delta x's, the width is 1. So this shows that delta x is equal to 1. Same for all of them. And then you just use the heights based on the right side of them. The area should be approximately these 1, 2, 3, 4, 5 rectangles. So A1 is here. A2 is here. A3 is here. A4, and then A5. So the first one has a width of 1 and a height of 1, so that's 1 times 1, plus. The second one has a width of 1 and a height of 4, so 1 times 4, plus. Third one has a width of 1 and a height of 9, plus. The fourth one has a width of 1 and a height of 16, plus. The last one has a width of 1 and a height of 25, which is 1 plus 4 plus 9 plus 16 plus 25. 5 and 9 is 14, plus 16 is 30, plus 25 is 55. So that was an overestimate. And I mentioned earlier that the exact area is actually 41 2/3. And if you average 55, and 30, you get 42.5, which is only 0.9 away from the actual answer. That's why I said one of my favorite things to do. It's just a simple concept in terms of numerical mathematics. I love just averaging the left and right hand anchored versions of these. When you're doing computational math, again, this is something we're not going to be doing in here, but it's still important to appreciate the actual analytical calculus. Because like I said, the first picture, that very first one, when it was just a boring old rectangle or a series of rectangles, you know the geometry formula for that one. When it's a triangle, you know the geometry formula for that one. And we know a couple other ones, but we don't know infinitely many geometry formulas. We don't know a geometry formula that would tell you the area under a parabola or any of these other really kooky, crazy curves. So that is why this is so important. So in a real calculus class, we show you how this Riemann sum, how this thing right here, you use a sum notation, you show that it turns into an integral and everything is hunky-dory. Fortunately for us, we just kind of use observations and leaps of faiths. Well, we observe that, hey, we got geometric answers to match answers using a calculus formula, so it must mean that integration gives us area under a curve. And it does. All right, so once again, in the spirit of the fact that we have a test coming up, I don't want to get too far ahead. I don't want to end up 3 and 4 sections past where we're testing on. So I want to go ahead and call it here. Having finished 4.2, which is a section that I am not going to officially test you on because the problems are these types of things, but generally in the homework, these delta x's aren't a 1, they're much smaller, which makes the problems much more of a headache. Again, if this was a true calculus class, we'd be doing these for a week or two. In summer, a week. I don't want to say 2 weeks. So next class, we're going to go straight into actually using the integral formulas and finding an area under a curve. I'm just going to say spoilers. 4.3. This is what it ends up looking like. We take this integral symbol with our f of x dx, and all we do is we attach those left and right hand numbers, like the 0 to 5, below and above that little integration snake or S or whatever you want to call it. So in the next section, we will actually find the area under the curve for x squared, doing an integral, and then it's really just plugging in these two numbers in somewhere, but we have to know what to do. And we'll geometrically reason that out next time. So on that note, if you don't have any questions, we'll call it a day. Please shoot me an email if you do have any questions. Don't forget that your test review is available. It is in Canvas. It should be under the last bit of Chapter 3 homework, so it should be pretty much the last or next to last assignment you can even see. Remember that my reviews are built to be very similar to the test. If you can handle the review, you should be able to handle the test. Remember, this is supposed to be your own work, no notes, no books. You can use a calculator, but analytic work is still important because any potential partial credit is going to be based on work that you submit. And if you just put everything in a calculator and you're submitting a blank page, you're not going to get any partial credit if you mess something up. So please understand that. Know your homework due dates. Have a good one. Have a good weekend. Study hard, work hard, put in those 8 to 9 hours. Get the test done. See you on Tuesday. Take care.